Okay, the next question, 79th question in code Q is two capacitors C1 and C2 are charged to 120 volt and 200 volt respectively. It is found that by connecting them together, the potential of each of one then can be made zero. Then what is the relationship between the capacitors? Now the circuit would be like this. Two capacitors C1 and C2 are connected to each other. If the charge on them becomes zero, that means the positive plate of one should be connected to the negative plate of another. And the total charge on each of the connected plate would be zero. That means Q1 will be equal to C1 multiplied by V1. That comes out to be 120 C1, and Q2 would be equal to 200 multiplied by C2. So the magnitude of the charge should be equal and opposite. That means Q1 should be equal to the magnitude of Q2. That comes out to be 3C1 equal to 5C2. That means the answer is 1. The question number 18 code Q is that a hoop of radius r and mass m rotating with an angular velocity omega naught is placed on a rough horizontal surface. The initial velocity of the center of the hoop is 0. What will be the velocity of the center of the hoop when it ceases to slip? Let's try to understand the situation. This is a horizontal rough ground and the hoop is initially rotating with angular velocity omega naught. Obviously it will try to slip on the surface. So when it will try to slip on the surface, the point of contact will try to go in the backward direction, so there is a friction force that is acting in the forward direction. So this friction force will be kinetic friction and it will try to push the hoop in the forward direction. After some time, the situation will be such that this will acquire a velocity v, and because of the torque due to the friction, the angular acceleration alpha will be in the opposite direction, so angular velocity reduces. We know that relative to any point on the ground, the torque of the friction would be equal to 0. So we can say that the angular momentum would be constant. The angular momentum initially was equal to mr square multiplied by omega naught. Finally, angular velocity would be equal to, angular momentum would be equal to mr square multiplied by omega plus mv multiplied by r. So we know that if it ceases to slip, then v equal to r omega, that is equal to m r square multiplied by v by r plus mvr. This means that r gets cancelled with r, so m gets cancelled with m, r again gets cancelled with this r, so we get v equal to r omega naught. The answer is okay. The question number 81 in code Q is an ideal gas enclosed in a vertical cylinder supports a freely moving piston of mass m. The piston and the cylinder have equal cross-sectional area A. When the piston is in equilibrium, the volume of the gas is V0 and its pressure is P0. Piston is slightly displaced from the equilibrium position and released. Assume that the system is completely isolated from the surroundings. The piston executes simple harmonic motion with what frequency? Let's try to understand the situation. Here there is a piston which is enclosing a gas at pressure P0. The atmospheric pressure is PA. So we can say in this particular position it is in equilibrium. Suppose if I displace this body from the equilibrium position by a distance x, in that particular position we can say the force, the body will not be in equilibrium. Initially it was in equilibrium, that means mg plus P atmosphere multiplied by area should be equal to P naught multiplied. Finally speaking, I can say the new pressure would change to P. So the new situation would be mg plus P atmosphere into A minus P naught multiplied by area will be mass multiplied by acceleration. So this is minus P into A. If we want to find out P, then we can use the equation for the adiabatic gas. We can say P into V naught minus AX or gamma will be equal to P naught into V naught to power. That makes P equal to P naught into V naught upon V naught minus AX whole to power gamma comes out to be P naught into 1 minus gamma AX upon V naught using binomial expansion. So when we substitute it over there, then acceleration comes out to be, mass into acceleration comes out to be mg plus P atmospheric into area minus P plus P naught into 1 minus gamma AX. Right? So this means this mg plus P atmosphere into area is equal to P naught into area. So this means this gets cancelled with this, and in other words, plus this is acceleration equal to minus P naught gamma A square into x upon V naught m, and we know in SHM acceleration equal to minus omega square x. So omega comes out to be root of P naught gamma A square upon m V naught, which gives us the answer as 2. Okay. Question number 82 of code Q is a charge Q is uniformly distributed over a long rod AB of length L as shown in the figure. Electric potential at the point O lying at a distance L from the NA is. Now this question can be easily solved by dividing the entire rod into small elements and finding the potential due to each element at point O. Figure goes like this. The rod, let's say we consider a small element at a distance x, point O, which has a length of dx. That means dV will be equal to k dq divided by x. dq happens to be q upon L multiplied by dx, whole thing divided by x. Then integration of this gives us the total potential. Here x varies from L to 2L. So the limits of integration go from L to 2L. Means kq by L multiplied by ln2. That would be the correct answer. So of all the 4 options, answer is 3. The question number 83 of code Q is a circular loop of radius 0.3 cm lies parallel to a much bigger circular loop of radius 20 cm. The center of the small loop is on the axis of the bigger loop. The distance between the center is 15 centimeter. If the current of 2 ampere flows through the smaller loop, then the flux linked with bigger loop is what? So to understand this question, we have to first of all find out the mutual inductance of both the loops. The figure goes like this. Here there is a bigger loop and the centers are at a distance of 15 centimeter and this is a smaller loop. Now we know that the magnetic field due to each and every magnetic field due to the smaller loop at different points of the bigger loop is not possible to be found, but we can find the magnetic field due to the bigger loop at point of the smaller loop. Let's see how do we do it. We can say B equal to mu naught I into R square upon 2 R square plus X square to the power 3 by 2. The power 3 by 2. That means this will be equal to mu naught I multiplied by, so R square upon 2. R square has value of 20 centimeter plus X square is 15 centimeter, the whole square whole to power 3 by 2. Now this will produce a flux. Flux phi will be equal to B multiplied by area of the small loop, that is B multiplied by pi R square. So that will make we know that this flux is equal to mutual inductance multiplied by current I. The mutual inductance comes out to be mu naught pi small r square capital R square upon 2 into R square plus X square to the power 3 by 2. So once we have mutual inductance, then the flux phi through the second loop due to 1 will be equal to same mutual inductance multiplied by current into 1. So by plugging in the values, we get the value as 9.1 into 10 to the power minus 11. Answer is 4. Okay. The question number 84 of code Q is, if a piece of metal is heated to a temperature theta and then allowed to cool in a room which is at temperature theta naught, the graph between temperature T of the metal and time t will be closest to. Newton's law of cooling states that dt by dt, the rate of change of temperature, is equal to C into T minus T naught. Put a minus sign because the temperature will be decreasing. So that gives you dt upon T minus T naught equal to minus C dt, and by integrating both the sides you get ln of T minus T naught upon T1 minus T naught should be equal to minus Cp. It means the temperature varies exponentially. So exponential variation of the temperature is denoted by this. After a very long time, it will tend to reach the temperature of the surroundings, that is theta. Answer of this question is question number 85 is asking for the IV characteristic of an LED. We know that light emitting diode is after all a diode. So since this is a diode, its IV characteristics should be same as that of a diode. Normal diode has IV characteristic as. So from the options it is very obvious that the only possible option is that of 4, and we can say that the energy of blue photons greater than the energy of the red photons. So that means they will require a higher voltage to get to the characteristic extreme curve. So that means the blue part will be at higher voltage as in comparison to the red voltage, the voltage corresponding to the red color. That's why the graph is 4. So the answer is